Hi everybody, welcome back. We are here to finish out chapter 2, and the last thing I want to talk about is something called, or is basically another definition of acids and bases. This is going to be the Lewis definition of acids and bases, and it's a little bit different but fairly similar in some ways to the Bronsted definition, right? In the Bronsted definition, everything was in context of protons, right? Whether you accept or donate protons, all right? The Lewis definition is going to have to do completely with what happens to electron pairs, all right? So, first let's define what a Lewis acid is. I'm just going to use La for short, Lewis acid. All right, a Lewis acid is defined as an electron pair acceptor. And a Lewis base is known as an electron pair donor. All right. Now, a lot of people get the Bronsted definitions and the Lewis definitions mixed up. There are some similarities. There are some differences. Let's talk about Lewis bases first. All right. Here's something that is pretty easy to remember. Lewis bases and Bronsted bases, they're interchangeable. In other words, for one thing, I'm not going to have enough room to write this word. There we go. This means that basically they are one and the same. If something is a Bronsted base, it's also going to be defined as a Lewis base. All right. So, for example, if we had something like OH minus, right? We know that's a Bronsted base because we said it's capable of accepting a proton, an H+. Why is it capable of accepting a proton? Well, it's because it has available unshared pairs of electrons that it can donate to a proton, right? So you see here, in the process of accepting a proton, the OH minus donates an electron pair. So therefore, it is a Lewis base, right? NH3, Bronsted base and Lewis base. CH3OH, Bronsted base and Lewis base. All right. The most common situations in which you see Lewis and Bronsted bases is when they have unshared pairs, but they don't have to be the only things that can act as Lewis or Bronsted bases. You know, something like this. Bronsted base and Lewis base, right? Because if you had an H+, that H+ could be donated to a pair of electrons that were not unshared but were pi electrons, right? So you could end up with something like that. And the extra hydrogen would be on this carbon attached by these electrons that were donated. All right? So that's a nice, easy part of the Lewis definition. If something's a Bronsted base, you can automatically classify it as being Lewis and vice versa. Lewis acids are going to be a little bit different. Here's something that you can remember. All Bronsted acids are Lewis acids. If anything qualifies as a Bronsted acid, it's a Lewis acid. And that makes sense, right? Because what do all Bronsted acids give up? According to the definition, they're proton donors. So all Bronsted acids give up H+. By definition, H+, what does it want to bond with? It wants to bond with electrons. It wants to accept electron pairs, right? So this guy right here is an electron pair acceptor. So yeah, anything that's a Bronsted acid is also going to be a Lewis acid. Whoops. Didn't mean to scratch that out. I meant to erase it. There we go. However, the reverse is not necessarily true. Not all Lewis acids are Bronsted acids. In other words, you can have things other than H+ that can accept electron pairs. Here's an example. Let's say we had boron trifluoride, BF3. All right. Whoops. Let me redraw that. All right. Now, if you look at BF3, I can tell you that BF3 is a Lewis acid. Okay? Is BF3 a Bronsted acid? Well, heck no, it's not, because guess what? It ain't got any protons, right? It can't act as a proton donor because it doesn't have any. But yet, it can still accept electron pairs. The reason being is because if you look at boron, count how many electrons boron currently has in its outer shell. You're going to see 2, 4, 6 electrons, right? This one of those that we talked about in Chapter 1 that was capable of existing with an incomplete octet. And it actually exists in neutral state, right? However, its outer shell can hold 8. It's got room for another pair. So, if something came along, let's just say we had water, that had available electron pairs, those electrons could form a bond with that boron because it's got extra room in its outer shell. Right? The electrons would be donated from water. That makes water the Lewis base. And if you look at the product, it's going to look like this. Now the oxygen is attached to that boron with that pair of electrons. Boron was neutral, right? It's gaining electrons now, so now boron is going to go negative. Oxygen was neutral. Now it's sharing some of its electrons that it wasn't before, so it's going to have a positive charge. So this is your Lewis acid-base product. All right? So you can see here, BF3, good example of something that is a Lewis acid, but is not a Bronsted acid. All right, let's take a look at another one. Right, we could take a look at this one. Another common Lewis acid that we use in organic chemistry, aluminum trichloride. You'll use this one in organic too. Aluminum trichloride, again, very similar to boron, right? You see this aluminum only has 6 electrons in its outer shell. It can accept another pair, right? So, if another Cl came along, and let's say it was a Cl minus, right? Just a Cl minus floating along. It's got a ton of extra electron pairs, just like we saw with water in the last example. It can lead in, form a bond by donating its electron pair to aluminum. And now you have this, right? The aluminum was neutral. It's now getting extra electrons, so it goes negative. The chlorine was negative. Now it's sharing electron density, so it goes down to being neutral, right? Within these acid-base reactions, going from reactants to products, charge in equals charge out. Total charge on the reactant side must equal the total charge on the product side. Okay? This is a good opportunity also to introduce a couple of other terms, right? In this case, aluminum trichloride would be referred to as a Lewis acid, and Cl minus would be referred to as a Lewis base. There's a couple of other terms that we can apply as well. We can also call Cl minus here a nucleophile. We can also call aluminum trichloride here an electrophile. All right. Let me explain the definitions of these names. Let's look at the suffix first, phile. The suffix phile means loving. All right. And let's take a look at nucleophile. Nucleophile literally means nucleus loving, right? It's something that is attracted to basically a nucleus, right? And what is a nucleus? It's something positive or partially positive, right? something that electrons can bond with. So this is looking for something positive or partially positive that it can bond with. And this aluminum just happens to be partially positive because it's got all these electronegative Cl's around it. Okay? An electrophile is just the opposite. It's electron loving. So electrophiles are looking to bond with something that's negative or partially negative. And you can see here the Cl minus is negative, so that's what bonds. Okay? So the terms Lewis acid, Lewis base are largely interchangeable with the terms electrophile, nucleophile. There's one caveat. Whoops. If something's a Lewis base, it automatically makes it a nucleophile. All right, let's see, I'm trying to find the best way to phrase this because it's a weird bookkeeping type of classification system. Non-proton donating Lewis acids are also known as electrophiles. In other words, as long as your Lewis acid isn't also a Bronsted acid, then it can be classified as a nucleophile, right? H plus, it's a Lewis acid, it's a Bronsted acid, but it's not classified as a nucleophile. Why? I don't know. It's just a bookkeeping thing that somebody else came up with, but it's something we should remember, right? Aluminum trichloride, Lewis acid, and electrophile. BF3, Lewis acid, and electrophile. HCl, Bronsted acid, Lewis acid, but not a nucleophile. Excuse me, not an electrophile, sorry. Okay? So, that's important to remember because in future chapters, once we get to chapter 7, I believe, we'll talk about something called nucleophilic substitution, and that will help us really see the importance of how nucleophiles and electrophiles can interact with each other to make new bonds. Okay? And that's basically it. That's all the new material that's left over. That completes chapter 2. I'll do a couple more examples with you just to make sure that you have a feel for it. And I'll do a couple out of the book. Let's see. Let's say we have this. All right, so this on the left is actually called diethyl ether. It's the one with the oxygen. We're going to be reacting it with boron tribromide. All right, so if you're looking at the mechanism here, again, you want to identify what's going to have electron pairs to donate and what's going to have room to accept electron pairs. All right, I think you can clearly see that we have available electrons here. This boron, just like in a previous example, is capable of accepting a couple of other electrons in this outer shell, so you end up getting this. Okay? Boron was neutral, it's accepting electrons, it becomes negative. Oxygen was neutral, now it's having to share some electrons, so it's positive. So that's your product. If we wanted to classify these guys, the diethyl ether on the left, that is definitely our Lewis base because it's donating electrons. It's also going to be classified as a nucleophile. Boron tribromide, it's accepting electrons, so it's a Lewis acid. All right. It's a Lewis acid that's not a Bronsted acid, so you can also classify this as being an electrophile. Okay? All right. Okay. Let's try another one. Let's try this one. Okay. So in this case, we have hydronium ion, H3O plus, reacting with the guy on the left. That is actually a type of molecule called a ketone. All right. And this is going to be a case where we can sort of mix the two definitions of acids and bases, right? This H3O, hydronium, as you guys have learned in Gen Chem, it's very much acidic, right? So it's going to want to give off a proton. And this proton can be plucked off with the electrons from that oxygen. Okay. So it's going to give that an OH and make it a positive charge, all right? And it's going to leave behind water. Like that, okay? We see in this case that, the ketone, it's accepting a proton, so it's a Bronsted acid, and it's also a Lewis acid. Oh, shoot. Hold on. That's wrong. Gosh, how embarrassing. And since I've already made most of the video, I don't want to start over, so I have to correct myself. It's actually a Bronsted base and a Lewis base. Ah! Okay. Yeah, sorry about that. Accepting a proton, proton acceptors are Bronsted bases. Electron pair, it's donating an electron pair to H+. That means it's a Lewis base. All right. Vice versa for this one, you're giving up a proton, so it's a Bronsted acid. That proton is in the midst of accepting electron pairs, so it's also a Lewis acid. All right. Because we have proton transfer here, and we have Bronsted acid-base terminology and reaction going here, we don't use the whole nucleophile, electrophile classifications. Okay? All right, that is it for Chapter 2. Be sure to get some practice, finish up your sapling, and let me know if you have any questions. Hope you guys have a great weekend. Bye-bye.